Welcome guys to today's lesson on numeric systems and binary representation. So what a number system? A number system is a way to represent number using a specific set of digits or symbols. In computing, we use different number systems because computer process and store data in binary format, while human beings typically use decimal. Understanding various number systems help us bridge the gap between human and computer language. So decimal, the common number systems in computing. We have decimal. Decimal system is what we use in everyday life, which uses a digit from 0 to 9, which is actually called base 10. Then we have binary, the fundamental system used by computers using only 0 and 1, fondly called base 2. Then we have octal. Octal often used in computing as a compact way to represent binary numbers using digits 0 to 7, what they call base 8. Then we have the hexadecimal, commonly used in programming and computer science, using digits 0 to 9 and letters A to F. So these are the common number systems in computing. Now, binary number system. Binary number system is a base 2 number system using only 2 digits, 0 and 1. It's crucial in computing because digital circuits can easily represent two states, either on or off, or high or low voltage. Each binary digit, each digit is a binary number, represent a power of 2, starting from 2 raised to power 0 on the right side and increasing to the left side with 2 raised to power 1 and so on and so forth. So over here, if you look here, you see that we have 2 raised to power 0, which is the first digit. The next one is 2 0 raised to power 1. So its state, actually, binary number is used to represent 0, which is off, and 1, which is on. So this is the two states we have in a binary number system. So binary to decimal conversion. To convert binary to decimal, we write out the powers of 2 for each digit position. Multiply each binary digit by a corresponding power of 2. Then we'll sum up all the results. So over here in our example, if you look at our example, we have our binary digit over here and want to convert it to decimal. Conversion means we want to check this number now in binary, which is what computer system understand. What is equivalent in decimal in our own number system? Now, this is computer number system representative of the number system of the computer, but we want to know what is the number in our own language or in our own number system we are using, which is base 10 decimal. So the best thing to do is to write out the number, then you write out the powers of those numbers, which is this position of this digit is 2 raised to power 0. The position of this one is 2 raised to power 1. The position of this one is 2 raised to power 1, 2 raised to power 2. This is 2 raised to power 3, 2 raised to power 4. If there are more digits, that's how you increase the 2 raised to power 5, 2 raised to power 6, 2 raised to power 7, and so forth, and so on. So when you have done that, then you multiply each of these positions by the digit that you are seeing here. So if this is an off state, you multiply, which is 0, 0 times that digit number. Then if this is an on state, you multiply the digit there, which is 1, times the digit position. So when you are done multiplying it, you now sum up all the results. So if 2 raised to power 0 is 1, then 1 times 0 is 0. You write down your figure here. 2 raised to power 1 is 2. 2 times 1, 2. You see the figure here. 2 raised to power 2 is 4. 4 times 1 is 4. You put it down. Then 2 raised to power 3 is 8. 8 times 0 is 0. You write down 0 here. 2 raised to power 4 is 16. 16 times 1 is 6. So when you sum it up, you now have your total value. So if this is summed up, we have 22. So the equivalent of this binary figure here in our own decimal place is actually 22. That's the figure. To convert our decimal to binary too, because sometimes you may want to convert our own readable language to binary. So how do you do that? You divide the decimal number by 2, keep track of the remainder, whether 0 or 1. So if the remainder is 0, you write 0. If the remainder is 1, you write 1. So that is actually what we do at each process. So continue dividing the quotient by 2 until you reach 0. So you now read all the remainders from the bottom to up. So in this our example, what we'll be doing is we'll be dividing by our decimal is 13. So we want to check the binary of 13. So 13 divided by 2 is 6, remainder 1. So you write down the 1. Then now divide 6 divided by 2 is 3, remainder 0. You write down 0. Then this is 3 divided by 1 is 1, remainder 1. So you write down 1. Then 1 divided by 2 is 0, remainder 1. You put down the 1. So over here, if you look at the binary here, you see that what we have is 0. We are taking it up this way. So we see you have 1, 1, 0, 1. So that is the binary figure of binary conversion of the decimal number 13. So if we are to convert it back to decimal, some people say, how do we get it? So now this is place value of 2 raised to power 0, so which is actually 1. Now this is actually 2 raised to power 1, which is 2, but it's off, so we don't actually need the value here because it is turned off. Then this is 2 raised to power 4, 2 raised to power 4, which is on, so we'll say okay, 4 plus 1, that is 5. Then this is 2 raised to power 8, so 8 plus 5 give us 13. So you now see that if you do whichever way you do, this binary number is correct. So binary arithmetic, we're looking at the addition of and subtraction of binary numbers. So the addition actually follows similarly with the division addition, but the only 2 digits. So we have 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, then 1 plus 1 is 0. You now carry 1 to the next set. So, but this binary subtraction is often done using two complement a method, which we'll be looking at. So here we have 0 plus 0 on the addition is 0, 1 plus 1 is 0, you carry 1 over here. So the 1 will bring over here plus this 1 is 0, carry 1 over here. We have 3 ones. So let me turn on my pen icon. So we have 0 plus 0, 0, 1 plus 1. We actually write 0 because there's nothing like 10, it's just 1 and 0, which is it has gone to the 2 place. So we have 1 and 0. So that other one, we write down the 0, take 1 here. So we now have 1 here. So 1 plus this one is 0. Now we still have a remaining one that we are carrying over to here. So we now have 3 ones here. So this 1 plus 1 plus 1 is actually 1. The remaining one, we take it here and we write it down here. So this is for the addition. Then the subtraction is actually more complicated a little bit. So we have 0 plus 1 can go normally in our addition. So we borrow. So we are going to borrow from this one. So when we borrow, we cross this. So when we borrow 1, this now becomes 1 and 1. We have 2, 1. So we have 1 and 1. So we'll now borrow this one over here. I'll cross it and bring it here, which is actually 1 and 1 again. So this 1 and 1, this one will cancel this one. So this one that's remaining is what comes down here. So now we have we cancelled 1, which we take over here. So we have 1 remaining. So this 1 minus this one give us 0. Now this one is already 0. So we're gonna borrow, this is 0 already. So we'll borrow 1 from here and come here. So have 1 and 1. Then when we do that, so this 1 minus this one will have 1. So this one comes down. So this is actually how we do our subtraction. So then this is 0 already because we have borrowed 1, 0, 0 minus 0 is 0. But actually in normal binary, I just left it here so it not look like confusing. But in normal binary, this 0 is not supposed to be here. We are not supposed to have a leading 0 in your binary number. So this subtracted this, we have 0, 1, 0, 1. So this is actually the binary subtraction. So sign magnitude. Use the leftmost bits to represent sign, which is 0 for positive and 1 for negative. So we have two complements more common in computers. Invert all bits, then add 1 to the result. 2 complement follows for easier arithmetic operations in hardware. So our arithmetic operation which the CPU does on our computer uses this. So what we'll be looking at now is how to represent minus 34. So the 34 we converted, but this is the binary figure of 34. But what if this is actually the positive number? What if it's a negative number? How do we do that? Over here is just simple. So we have to do an inverse of whatever we have here, which is what the computer does. So which is 1 complement. So 1 complement of 34 plus is actually opposite of this. So this side we have 0. So over here to be 1. Here we have 1, it will be 0. So you are just inverting whatever values you have on this positive number of 34. So when you invert it, you have 0, which is 1, 1, which is 0, 0 is 1, 0 is 1, 0 is 1, 1 is 0, 0, 1, 0, 1. Then when you are done doing the first complement of the positive number of 34, you now do the second complement, which is adding 1 to your result. So when you add 1, you have 1 plus 1, which is 0. You carry 1 here, then you bring down all the remaining ones and 0. So if you watch here, this actually signifies that this is actually a negative number of this figure. So this is actually how you represent negative numbers on binary. Real numbers in computing. So we have floating numbers and they represent real numbers in computing, similar to scientific notation. So over here we have 1.0001111 times raised to the power 2. So this raised to the power 6 is actually the same thing as taking this over here and giving its normal value. So this is the exponent of this, so which is equals to this and is equal to this. This is equals to it. So if you take it down here, you now have this in base 2, and if you convert it to which, if you convert this, you have 79 in base 10. So this is actually how we represent floating numbers. Applications of binary. Some will be asking, where do we apply all these numbers you're looking at? So you apply it in data storage. Many times I've asked my students, when you are teaching binary, to look like a boring subject, but boring topic. But most times when you now tell them, okay, I want you to divide my hard disk partition into two partitions, so into 3, 1 hard drive, you divide into logically 3 partitions. That is where you now say, oh, binary needs to be played. Or when you are downloading file from the internet and you are seeing 10 megabytes per second and you want to download something of 1 gig, how long will it take? So this is actually where we need to put the binary. Some places we put binary into, you almost use it in every day, but you may not know that this is actually what you are doing. So you use it in data storage. All data in computer is ultimately stored in binary. There's no data that is not stored in binary. The base unit of data in computer is actually bits. So they are all in bits. Then or byte. Byte is 8 bits. So this is actually the unit of storage in data. That's why you see you have megabyte, gigabyte, terabyte. All of them are measured in bytes. So they'll have digital logic. So this actually is actually used on all digital circuits like your microwave, your fridge, on and off. Most times when you open the door of your fridge, light comes up. When you close it, the light turns off. So this actually a binary state which is using digital logic. Then you also have it in networking where your IP address is actually in binary format internally. You are seeing the hexadecimal format, but internally what you are seeing, what the computer is uses to recognize your binary, your IP address is actually in binary. So these are places that you can actually apply this basic computing, binary computing we are learning. So for those that are looking for something they need to try, so put this knowledge into practice. So here you just try converting the following. So you convert this binary number to decimal. Over here, this binary number, convert it to decimal. Then let me erase out. So you convert this number, convert this binary number to decimal. Then you convert this decimal to binary and also perform a binary addition of these two numbers. So this is actually what you try. I would like to see your result. You can actually drop it in the comment section or you go over to the classroom and show me your workings. I would love to see that. I can't wait to see your practice exercise solutions. Yeah, we have come to the end of today's lesson. So binary is the fundamental of all digital computing. So understanding number system is crucial for computer science and engineering. So proficiency in binary operations and conversion is essential for many aspects of computing, from low-level programming to understanding how data are represented on your system. So these are actually the most reason why we look at binary today. And thank you for your time. We'll meet in the next lesson.